Hello there guys, and welcome back to another epic inexorable maths video. In this video we're looking at using the product rule for differentiation for the product of 3 or even n functions. So essentially, let's say that we want to differentiate something that looks maybe like this. Let's say that we have y equals x e to the x sine x. How would you differentiate that? Because you might say, well, it looks maybe like the product rule, but it's, how are you supposed to do your u and your v, or your g of x and h of x, or whatever you label it? How are you supposed to do this when you have 1, 2, 3 functions? You have an x, an e to the x, and a sine x. How are you supposed to do this? Well, there's 2 ways that we can sort of derive a little formula that will allow us to answer questions like this. But also, we can answer questions that look like this, or maybe even something else. So maybe we can times that by the natural log of x, that by 1 plus x cubed, or something like that, to the power of 4. I'm making it completely up. And you can actually have, any number of terms here. You could times this by hyperbolic sine, which you might not have seen before, but this doesn't matter. I'm just labeling random stuff. You could differentiate this whole thing. So how do you do it though? How do you do it? Well, let's have a look at some formula. So imagine that we have y, and y is the product of 3 functions. Y is equal to some function u, that's a function of x, multiplied by some function v, which is also a function of x, multiplied by another function, we'll say w. So normally when you use the product rule, which I'll leave in the description below, the link to that video, normally you have a u and a v. But now we're going to say we have a u, a v, and a w. Maybe the u is x, maybe the v is e to the x, maybe the w is sine x. It doesn't matter, it could be anything. But normally you have 2, now we've got 3. What's the derivative of this? What's the product rule for this? Okay, so you can do it in 2 ways. I'm going to show you the logarithm way first, and then I'll show you another way in a second. So what we do is we use implicit differentiation, just like how we do the normal product rule, take natural logs of both sides. Now, if you take the natural log of u, v, w, this is equal to the natural log of u plus the natural log of v plus the natural log of w because of logarithm rules. If you have a logarithm with a bunch of things timesing together inside, you can split it up into a sum of individual logarithms. So this is totally legit. You then differentiate both sides implicitly. The derivative of the natural log of y with respect to y is 1 over y, and then we times that by dy dx because we did it with implicit differentiation. The derivative of the natural log of u with respect to x is going to be 1 over u times du dx. Again, this comes from implicit differentiation. I'll leave that link in the description of this video as well. And same goes with v, so 1 over v dv dx plus 1 over w dw dx. Okay, and then all we want to do is rearrange this to get dy dx on its own. So we're going to multiply both sides by y. But remember what y is. Y is u times v times w. So we're actually going to multiply both sides by u times v times w. And that gets multiplied by the rest of it. So 1 over u, du dx, etc. I'll just cut to when I've written all of that down. Okay, there it is. It's all chilling out right there. And then we're going to just expand this out. So notice how the u and the u cancels with that first term there. So we end up just getting v, right, I'll write it this way around. I'll write it as du dx times v times w. Second term, the u v w times is by the 1 over v dv dx. The v and the 1 over v cancel out. So you end up with adding u dv dx w. And then finally, the w and this 1 over w in the last term, they cancel out. And you end up with u times v times dw dx. And actually, this is the kind of triple product rule, if you will. This is the product rule for the product of differentiating 3 functions. It's this. You might say, oh, whoa, that's a bit confusing, it's a bit weird. It's not. All it is you times all of the functions together, and you individually differentiate one of the functions each. So, for example, we'll do an example right now. Let's say that we had y equals x e to the x sine x. We would differentiate the first, so the derivative here, We'd say, okay, well, leave the last two terms, differentiate the first one. X differentiates to 1. So this would be equal to just 1 e to the x sine x. And then we're going to add the whole thing again, but we're going to differentiate the middle term this time. So x, the derivative of e to the x is still e to the x. And we're going to leave the other two. And then the last term is we're going to leave the first two and differentiate the third. So it's going to be x e to the x cos x. Like this. And of course, if you wanted to, you could factorize it and blah, 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 blah. But that's how you would do it, essentially. Now, the other way that I'll show you to do this, to get the same formula, is to just consider this. So y equals UVW again. How do you get the same formula in a different way? Very interesting. I'll leave a timestamp in the description if you want to just skip to the nth term, but this is just a different way to derive the same thing, basically. So UVW, how do you differentiate this in a different way without logarithms? Let's say that you don't like implicit differentiation. Is there an easier way? Yes, of course there is. So what we'll do is we'll switch over to function notation, and I'm going to do the product rule, but I'm going to pretend that u times v is one function on its own, and w is another. So now this is the product of two functions again. It's u times v, that's one thing, times w. So it's two things. It's uv times w. Product rule. So, and again, I can't label these u and v because they're already in the thing. So instead, I'm going to label f of x to be u times v, and I'm going to say that g of x is the w. So I'm basically doing the product rule, but instead of doing u equals blah 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 and v equals blah blah blah, I'm saying f of x equals blah 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 and g of x equals blah blah. Just because I can't say let u equal uv and let v equal w, because it would just be really weird and confusing, and it's because you're using the same letters to represent different things. Don't worry about it. So we're just going to do f of x and g of x. That means that the derivative of this is the derivative of uv. Well, we know from the product rule what the derivative of uv is. The derivative of uv is u dv dx plus v du dx, or whichever way you want to write it. And the derivative of w with respect to x is literally dw dx. And then what we do is we do the product rule with this. So it's going to be f of x times g prime of x. So I'll write this down. Dy dx is equal to u times v times dw dx. So u v times dw dx. And then we're going to add g of x times f prime of x, which is going to be w multiplied by u dv dx plus v du dx. I'm not sure if my head is in the way, so I'm just going to move slightly over so you can see that. So it's g of x times f prime of x. This is literally the normal product rule, but just obviously, you know, sort of generalizing, pretending that one of the functions like is not a product, but it actually is a product. As a result, we get u v dw dx plus, and then if we expand this out and maybe change the order of the terms a little bit, you get u dv dx times w. That's the first term, but with the order of the terms just moved around a little bit. And the second term is w v du dx. I'm going to write that as du dx v w. Okay. And of course, you know, you can see this is the same thing. I've kind of written it in a different order. If you want to match it with the order that I wrote it originally, let me do that now. I'll cut to it. You end up getting this. So this is the exact same thing, of course, as what we had above. It's just a different way to get there. This one uses the fact that you already know the product rule. Strictly speaking, in order to really thoroughly derive this, you do need to use implicit differentiation. Because in order to do it the second way, we already assumed the product rule. And the product rule needs the implicit differentiation in the first place. So the first way that I showed you is probably a better way, but this way is quite nice because it doesn't involve any logarithms or anything like that directly. Awesome. So in general, if you want the nth, if you essentially have n terms, the product of n terms, maybe it's 10 or 100, if you want to differentiate not just the product of two things, you know, x e to the x or something like that, let's say again you have this massive chain of things, how do you differentiate it? You do this. You literally take every single term and you say, right, I'm going to differentiate the first term and leave all the rest as the same. And then I'm going to leave the first term, differentiate the second, leave all the rest the same. Third, and you just progressively move through. So if you want to take, if you have a y equals, and maybe it's like, I don't know, f1 of x times f2 of x, f3 of x, f4 of x times f5 of x, and each of these like f, like of, you know, every number, f of like f1 of x, f2, they're all just different functions of x, and they can go on for as many as you need, all the way up to like the nth one, so fn of x, okay? However many, imagine you're trying to differentiate this, and again, f1, f2, they just mean different functions of x, labeling them. Okay, imagine you want to differentiate this. The derivative would simply be f1 prime of x times the rest, so the normal rest, so f2 of x times f3 of x, all the way up to fn of x, and then you would add f1 of x, the original, times the second f of x differentiated, times, you know, f3 of x, original, all the way up again to fn of x. You just keep doing that all the way until you get to f of n of x, and you differentiate that last term. So you can see, you know, if you equate it to this one here, this 3 one, imagine this with 4 terms, you do the exact same thing, just keep going. And you can prove that for any n that you want, as long as you have the patience for it. You can just keep doing it. It follows the pattern all of the time. So that is essentially how you can differentiate any number of terms, all timesing together in one go. It's quite cool, very interesting. Thank you guys so much for watching, highly appreciate it, and I'll see you in the next video.